Good morning, students. Hope everyone is in good health. Today, we will discuss about band theory of solids. Before going to band theory of solids, let us we recap about free electron theory, which you have studied in your previous semester. So, as you know, first of all, to understand the conductivity of materials, Lorentz and Drude developed the theory that is classical free electron theory or Lorentz-Drude theory. It is basically depend on assumptions. See, the first assumption is a metal consists of positive ions. It consists of positive ions whose valence electrons are free to move between the ions, and forming electron gas. This is the first assumption. This classical free electron theory uses kinetic theory of gases. According to kinetic theory of gases, the kinetic energy of gas molecules is equal to 3 by 2 kT. Therefore, electrons are equivalent to gas molecules, hence kinetic energy of free electrons is equal to 3 by 2 kT. So it uses Maxwell-Boltzmann distribution law, that is MV distribution. Third one, the potential due to positive ion is considered to be uniform and hence electrons move with the same energy throughout the crystal metal. Fourth one, the mutual repulsion between electrons is ignored, and also the collision between electron and positive ion, that also ignored. See, based on this assumption, the expression for electrical conductivity is deduced as sigma is equal to n E square tau by m, where n is the concentration of electrons, E is the charge of the electron, tau, that is the mean collision time, m is the mass of the electron. So, here, if you observe this, the expression, we can observe that sigma is proportional to n, that is concentration of electrons. That means what? When you consider the trivalent metals like aluminium, which contains more electrons compared to the monovalent metal like copper, that means concentration of free electrons in aluminium is greater than that in copper. So that means it may say that if you use this relation, electrical conductivity of aluminium is more compared to electrical conductivity of copper. But in our practice, we know that copper is better conductor than aluminium. Similarly, when you consider the specific heat at constant volume, according to this classical free electron theory, Cv is equal to 3 by 2R. But experimentally, it is equal to 10 to the power minus 4 RT. So, in this way, there are large contradiction between the theoretical aspects and experimental value. Hence, this theory was discarded. So, in order to overcome the difficulties in this theory, in the year 1927, Sommerfeld modified this theory. That is, he retained the third and fourth assumptions of classical free electron theory, but modified the first two. According to quantum free electron theory, the energy of free electrons are quantized. That means what? According to classical free electron theory, all free electrons are having same energy at a given temperature T, that is equal to 3 by 2 kT. But here, at a given temperature, the energy of different electrons are different and it is quantized. That means what? The energy of electrons are visualized in terms of set of energy levels. So that means the free electrons which are moving inside the metal, that is equivalent to, they are present in a potential well. See, this is the case. This is the potential well. In this potential well, free electrons are present. So their energy values are quantized. That means different electrons are having different energies. That means they are quantized, means they are increasing in steps. See, electrons having energy E1, E2, E3, E4 and so on. So then the question is, how these energy levels are filled? To fill this energy level, we are using Pauli's exclusion principle. Pauli's exclusion principle. According to this principle, maximum of 2 electrons can occupy a given energy level. So that means one electron is clockwise spinning electron, another one is anti-clockwise spinning electron. So in this way, we can fill the energy levels. Third and fourth are similar to classical free electron theory. So that means 2 electrons having energy equal to E1, E2, 2 of them. Like this, you can fill the energy level. Finally, this is the last energy level. this is the maximum energy level, right? So this maximum energy level, that is uppermost field energy level, is called Fermi level. The energy corresponding to the electrons present in the Fermi level is called the Fermi energy. That means this is the situation we are visualizing at 0 Kelvin. So therefore at T is equal to 0 Kelvin, Fermi energy is the maximum kinetic energy possessed by the electrons. So this quantum free electron theory uses FT distribution law, that is Fermi-Dirac distribution law, according to which probability of finding the particle in a given energy level E is given by f of E is equal to 1 divided by 1 plus e to the power E minus EF by kT. So, using these concepts, we can explain the conductivity of electrons in the metal. Sigma is equal to Ne square tau F divided by m star. Here m star is the effective mass of the electron. Tau F is the mean collision time calculated for the electrons present in the Fermi level or nearer to the Fermi level. The main difference already we have observed here. One is energy of free electrons are quantized. Here quantum free electron theory. In classical free electron theory it is the same. Secondly, when you observe this expression, tau F comes into picture, right? We are not calculating the mean collision time for all electrons. Only we are calculating for the electrons present in the Fermi level or adjacent to Fermi level. That means what? According to quantum free electron theory, all free electrons are not conduction electrons. Only those electrons present in the Fermi level or adjacent to the Fermi level take part in the conduction process. Rest of the electrons are not taking part in the conduction process. Using this concept, we can successfully explain the resistivity of the metal is directly proportional to T. Cv is equal to 10 to the power minus 4 RT. Then dependence of this conductivity on free electrons, that also can be explained properly. We can explain thermionic emission. We can explain thermal conductivity of metals. All these factors can be explained using classical free electron theory. But main drawback of this theory is, in classical free electron theory also, we could not explain why some materials are conductors, why some of them are insulators, why some of them are semiconductors. Similarly, in quantum free electron theory also, we could not explain the classification of material into conductors, insulators and semiconductors. To overcome this difficulty, we are making use of band theory of solids. Band theory of solids. So, when you consider the band theory of solids, first of all, we must know what are bands. Just consider two identical atoms. Consider this is the valence electron. Say this is copper atom. Similarly, consider another copper atom farther away. Now, when these copper atoms are well separated, energy of this electron is E. This is also E. Now, I want to form a copper solid. What we have to do? We have to consider such n number of copper atoms which are farther away. By applying the force, you have to bring all copper atoms close together. So, now what happens when you bring the atoms close together? So that there may be overlapping of orbits. So when this happens, there will be the interaction between these two valence electrons. Therefore, the energy of one valence electron is decreased to E1. That of the second atom, the electron energy is increased by same amount, it rises to E2. That means if I write in energy level diagram, so before the application of the forces and you bringing the copper atoms close together, that means when they are farther apart, both electrons are having energy is equal to E. But when they brought closer, what happens? Energy of one electron is decreased, that of the other electron is increased by the same amount. That is, this is E1, this is E2. Right. That is, delta E amount decreased, delta E amount get increased. That means when you bring two atoms close together, single energy level split into two energy levels, E1 and E2. Similarly, when you bring n number of such copper atoms, then single energy level is split into n number of levels. They are very close to each other. It can form or looks like a continuum. So this collection of energy levels is called energy band. See, when we are discussing about the formation of bands, there are two approaches. So, first one is atomistic approach. So, in this atomistic approach, electrons are considered to be tightly bound to individual atoms. Tightly bound to individual atoms. As atoms close, we discussed just before how the bands are formed. As atoms brought closer, to form the crystal or metal, interaction between neighboring atoms take place, and the spread of energy levels takes place. So that means when you consider the electrons belongs to different shells, let us we represent this, whether the energy bands of K shell, L shell, M shell, etc. are of same width or different, right? So when you consider the K shell, which is the innermost shell, L shell, next, M shell, outer, like this it goes. When you bring the atoms close together, the interaction between the electrons belongs to K shell is less compared to interaction between the electrons belongs to L shell, because the separation between K shell is large compared to L shell. Interaction between L electron is less compared to M shell. That means there will be less energy spread in K shell compared to L shell. There is less energy spread in L shell compared to M shell. Energy is along y-axis, distance is along x-axis. So this is the reference point R0. So you are bringing, when the atoms are farther away, all electrons are having the same energy, but as you bring close together, what happens? Energy spread takes place. This is for K shell. See, this is for L shell. Energy spread takes place at here. Right. Similarly for M shell, so that is, this is E1, E2, E1, E2, E1, sorry, this is E1, this is E2. So E1, this is E2, right? Like this. So that means there is overlapping of bands takes place because of more interaction in M shell. This is the atomistic approach. Second one is one electron approximation. Second one is one electron approximation. So what it is? Let us you consider the lattice, that is, which consists of positive ions, so now here let us you consider the electron. So we are observing the electron motion. In this one electron approximation, we are considering the motion of one electron. This electron moves in the potential of positive ion. During its motion, due to the effect of potential due to positive ion, the energy of the electron get altered. Then what happens? Other free electrons are present. These free electrons influences the electron under consideration. Because of this, the energy of that electron undergo vary. So therefore, in one electron approximation, we are considering one electron and its energy variation or perturbation is observed due to the potential of positive ion and perturbation due to the cloud of free electrons. This is what we are how to discuss.